Ladies and gentlemen, would you like to take your seats? Thank you. So welcome to the third annual Luxton Memorial Lecture hosted by the University of Adelaide's Centre for Energy Technology. My name is Susan Jeans and I chair the Centre's Industry Advisory Board. The head of our centre, Professor Gus Nathan, will talk to us shortly about his mentor, Sam Luxton, and the history behind his lecture. But first, I'd like to say a few words about the reasons why Gus was so moved by Sam's influence on him that he worked to establish this annual lecture in his memory. And in honour of Sam, to ensure that those who are invited to present it each year are making an important contribution to the global debate on the future of energy. Sam Luxton had a wonderful influence on his students. He was the essential personification of the inspirational teacher to people like Gus. He encouraged his students to be curious, to find great things within themselves, and to strive to learn and to uncover more. The wonderful thing about this, for those of us who work with Gus, is that we see the very same thing in him. Gus has a wonderful, even-handed approach to his teaching and his research, underpinned by a deep personal commitment to the resolution of global energy challenges. He places high value on the contribution and the views of both his students and his peers to the problem-solving process, and he never lets you think that your view and your contribution isn't important. He inspires us to be better and to uncover more. Gus leads a team that is focused on one of the biggest global challenges of our time, how to reduce our emissions from energy. How do we use energy smarter? How do we use it less? How do we develop technologies and new materials that embody more inspired ideas and more collaborative processes? And of course, with less emissions. The Centre has a great depth of knowledge and potential that is highly relevant to these challenges. So teachers like Sam and Gus and the Centre's leadership see the connection between these important challenges and the potential of the bright young minds and to keep uncovering more. So now it's my pleasure to introduce one of the members of the leadership team, Professor Anthony Zander, head of our School of Mechanical Engineering. Anthony has worked in industrial research and development, consulting and academia. His research interests are in acoustics and vibrations, and he is a project lead on a number of energy-related projects dealing with gas pipeline venting through the Energy Pipeline CRC, of which the university is a member. Anthony is going to give us an introduction to the School of Mechanical Engineering and the Centre in the broader context of research in the university. So please welcome Professor Anthony Zander.
Thank you, Susan. Is this on? Or? Okay.
Everybody here?
This might be a bit cool. Okay. So welcome. Firstly, welcome to the Ghana lands on which the University of Adelaide campuses are built. We acknowledge and pay our respects to the Ghana people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and the relationship of the Ghana people to country, and we respect and value their past, present and ongoing connection to the land and cultural beliefs. So also, on behalf of the University of Adelaide, I welcome you to the university and to the 2017 Luxton Lecture. As head of the School of Mechanical Engineering, I'm pleased to be supporting this event. To give you some context, a large proportion of the staff and research students in our school are also members of the Centre for Energy Technology, providing inputs to energy-related projects in our areas of research strengths, including energy applications, thermofluids, acoustics, and wave energy. Energy technology is also one of our school's 5 interdisciplinary applied research themes, which also include humanitarian research, defence technology, biomechanical engineering and marine engineering. So to give you some idea, our energy-related work ranges from fundamental science at the nanoscale to large-scale applied engineering research, and is very much aligned with the University of Adelaide's research strategy of research for impact, which involves translating research into economic and social benefit. So I look forward to tonight's presentation by Dr. David Mooney and hearing more about some of the areas that might be ripe for further research with impact. Thank you.
Thank you, Anthony. hear me? Am I the right height? Okay, thanks. He has led the Centre in developing its vision, defining priorities and devising and implementing its strategic plan. Under his leadership, the Centre has identified novel approaches with strong potential to make a breakthrough in the delivery of low-cost clean energy technologies, and has engaged with partners spanning industry, international research institutions and government agencies. Professor Nathan is an ARC Discovery Outstanding Researcher who specialises in thermal engineering systems supplied by solar, geothermal and the combustion of fossil and biofuels. But he also works with hydrogen, wind and wave power. His recent work has focused on novel approaches to integrate and optimise these different energy sources. He's published widely, jointly authoring some 100 papers in international journals and 150 in peer-review conferences. Professor Nathan will now give an introduction to the Luxton Memorial Lecture, which has, as I have alluded to, a very personal significance to him. The late Professor Sam Luxton was both his mentor and his dear friend.
Thank you. Thank you, Susan, for those kind words, introduction, and it certainly is my great pleasure and honour to be able to say a bit about the legacy of Sam Luxton, Professor of Mechanical Engineering at this university. And obviously his photograph is up there. The key thing that you'll notice is he was not only a technician or technical person, but he also was involved in engagement in the broader community. I'm going to have to move this microphone because I don't have a screen in front of me. And so this is, I won't say all about him, but a couple of the key contributions that he did make is he was responsible for drafting an energy report to the Prime Minister in the 70s that led to what was firstly the National Energy Research and Development Corp that eventually evolved into ARENA, which is, of course, critical to Australia's future energy, and of course Susan is on the board of ARENA. He also was visionary in interdisciplinary research, establishing a program with chemical engineering, which was the precursor to what is now in the centre is even more interdisciplinary, but that was really pivotal in the evolution of our work in Adelaide. He was not only involved in research, but in taking research into solving industry challenges and contributing to those. And there are two of the major technology platforms. One of them is the gyrotherm low-NOx kiln burner, which is still in commercial production by a local industry partner, and it's great to have David Retallick and Jordan Parham here from FCT, have a long-standing partnership with this company. And another company, another technology, which also, this second one was a spin-off company that in air conditioning, which I'll say a bit more about shortly. But he established a culture of integrating science and technology together, which is about bringing not just, and also Peter Mullinger is also here, who's one of the founders of FCT, and bringing the research to meet the specific challenges of industry, not just blind research, but strategic research. And you see this is now continued today. So a couple of things about Sam's approach. He would engage with society to understand the challenges. And the engagement is a critical thing that we've tried to learn from. There's no point in trying to solve someone's problems for them. You have to work together. And then devise solutions to major industry challenges. Sam didn't believe in picking easy problems. He picked things that he thought would make a difference, and we try to do the same thing. And then partnerships are needed to implement the solutions, working with industry, and establishing strategic research programs. Whenever you do with new technology, there are some things that are understood, some things that are not. And so bringing the research to meet the challenges that can help to underpin the technological development, and inspiring his team. Sam had absolute confidence in us, and this is a culture that we try to propagate in our centre. So one of the technologies, I won't say too much about it, but this is a technology that he co-developed initially with Alan Shaw. It became known as the Shaw method from this, which was basically applied new understanding to how to modify turbulence to enhance condensation processes, and led to a technology which ended up being taken to the US, and out of that initially a Luxton Reed Centre was established. This is a multi-million-dollar technology industry which is still being applied today. The other one is the gyrotherm technology, which also came out of some of my PhD thesis, and Sam was also instrumental in linking industry partnerships, which provided the postdoctoral fellowship for me, and then the linkage with FCT with the people I've already mentioned. And this technology, of course, the reason it was developed is because it ended up having a significant reduction in NOx emissions, which was, I guess, at that time, the challenge of NOx was a bit similar to the challenge of CO2 today in terms of how industry was targeting, although, of course, the CO2 challenge is even bigger. The other technology which Sam was instrumental in assembling the team and getting us working on this project was the Olympic Flames, and Jordan was doing his PhD at the time. He's in the audience tonight, also one of Sam's mentees, I guess we would say. And the technology that came out of the Olympic Flames, of course, the whole team here at Adelaide worked very hard on this for many years, and Richard Kelso played a key role in this as well. But the technology that came out of this has spawned a new company which has supplied technology into every Olympic Flame since then, and David Ritalik leads that commercial work now. So this is some of the work that happened at that time, and you see Sam in one of the research meetings on the bottom left. But I think out of this, the words that have pretty much become cemented in history are, sure, we can make that thing burn underwater. And that was typical of Sam's belief. He wouldn't just say this out of blind thinking, but he had some ideas as to how he could see a very difficult challenge being met, and he believed the team could do it. And really, this is what we try to continue to inspire each other to continue that belief. So the centre now, the ongoing legacy that Sam has left behind, and I guess a key, many research groups come and go and they die when someone retires, but this has continued because Sam invested in people. And we have a very strong team throughout the centre, many people, some of the different types of technology you see of wind, of gasification, heliostat, aerodynamics. On the bottom right, we started with combustion. This is, on the bottom right, is a picture of some solar thermal calcination of alumina, which was recently demonstrated with our partners in Zurich, ETH. And so you see there's a big program which has grown out of Sam's vision. One of the technologies which is also indicative of the path of starting from combustion but bringing in solar thermal is this one, which Professor Bassam is now leading, which is, and also I see Alfonso, one of our postdocs, is also here in the audience tonight. The photograph on the top left, this technology has just been demonstrated in the lab. It's a way of integrating combustion into a solar thermal process so that you can maintain firm, continuous output, firm supply, particularly important for standalone units. And one of the partners we're working with, also Heliostat SA, is also shown there as being a potential way for meeting small to mid-scale demand of systems that can be standalone. But coming back to the concept of bringing research to meet the technological challenges, where the solar, maybe some of these systems, the concentrating solar and the flame, they can run independently, but there may be times when there's intermittent cloud when you run them both together. And in these conditions, high flux radiation is impinging on a flame. So this is a new regime that hasn't been understood before. So this is where the laser laboratories, which again Sam was instrumental in setting up, and since then we've built on these systems a lot. And Professor Ziad Al-Wahabi plays a key role in the laser systems development, and then a lot of us work in this. And these are some of the tools that we then bring to help to understand these challenges. One of the projects now we're working with, also meeting industrial challenges, is working with these partners down the bottom, including Alcoa, Hatch, IT Power, and some of the members from IT Power here today. and also University of New South Wales and CSIRO, looking at the challenge we're trying to meet is to find ways that are economically attractive of bringing between 25 and 50% solar thermal energy into the commercial Bayer alumina process, and we're looking at both the low temperature steam program and the high temperature calcination. This is a $12 million program, which we're now significantly in far enough to be really getting some exciting results, but a long way to go yet. Another big program, which is a national program, is the Australian Solar Thermal Research Institute, and some of our partners from UniSA, Frank, I saw here tonight, are part of this national program, and of course working collaboratively and nationally is critical. And the program which we're most involved in the University of Adelaide is the solar fuels work, and Greg Meether and Gunther from Flinders University are also here as part of that program, looking at ways of generating alternative fuels. We're targeting liquid fuels from a range of different feedstocks through the institute around alternative fuels production paths. So finally, I guess this has given a bit of a snapshot really as to why we host the Luxton lecture in Sam's honour, and we're really very, very excited that Dr. David Mooney has been able to come and give this lecture. The mix that he brings also is the mix of the technical background but the big global challenge, and so I won't introduce him now formally because Susan will do that, but we're very excited that he's been able to come and present this lecture in Sam's honour, and I'll hand this back to Susan to continue the proceedings. Thank you.
Thank you very much, Gus. And I love that photo of Jordan in the 90s. It's my pleasure now to introduce to you our speaker for the 2017 Luxton Memorial Lecture, Dr. David Mooney. Dr. Mooney is currently the Director of the Strategic Energy Analysis Centre at the US Department of Energy's National Renewable Energy Laboratory. Analysis at NREL aims to increase understanding of the interactions and roles of energy policies, energy markets, technologies, environmental impacts, and infrastructure in the deployment of clean energy technologies. This is a very important understanding of these interactions, and one that we're very pleased to have you here in Australia to talk to us across our institutes and governments about the challenge that we also face. Prior to his current role, Dr. Mooney was the laboratory program manager for solar technologies, where he was responsible for managing and coordinating NREL's $70 million solar R&D portfolio. While at NREL, Dr. Mooney also led efforts to identify and address technical issues associated with the large-scale deployment and integration of renewable and energy efficiency technologies into the existing infrastructure system. In this role, he led 180 researchers conducting $100 million in R&D annually. In these roles, Dr. Mooney has testified as an expert witness before the US House of Representatives Subcommittee on Energy and Environment, as well as before multiple state legislatures. Dr. Mooney is a 29-year veteran of the renewable energy industry and has a PhD in condensed matter physics from the University of Arkansas and a Bachelor of Science in Engineering Physics from the University of Tennessee. Welcome to Australia and welcome to Adelaide, Dr. Mooney.
Thank you. I noticed. Eliminate the feedback. Can you hear in the back okay? This actually seems too loud, doesn't it? Move this down just a little bit. Better?
Try that.
Okay, how's that? Okay, all right, we're set. Well, it's thank you so much for the great welcome, and it was already an honor to be here, and but now I'm inspired as well, having some more context about Dr. Luxton and what a brilliant career, and obviously what a great mentor he was, and so that coupled with being in the very nicest lecture hall I've ever had the privilege to speak in. It's really is a great pleasure to be here. and to share with you some of the dynamics of the energy markets in the U.S. and talk to you a little bit about how our system is transforming and hopefully make a few connections to the circumstances here in Australia. I think in the end we have a tremendous amount to learn from each other as we move our energy systems to low carbon or no carbon energy systems. So my outline is given here. I'll set a little bit of context by talking about the transformation in the energy system and talk to you specifically, though, about what's happening in wind and solar markets in the U.S. It's a really very exciting time. And then review a little bit about how the U.S. grid is structured and how it's operated. And then talk to you about an area of research that I've been involved in a lot lately, which is studies of future energy scenarios that look at operating the power system reliably under high penetrations of wind and solar technologies. We'll review a little bit about some of the policy drivers, both state and federal level, that have led to this, led us to the cusp of this transformation. And then just wrap up with some of what I feel like are some of the important lessons that we've learned and some of the takeaways that I hope you'll leave this with. So we'll start here. This is electricity production in the U.S. Shown by production technology going back to 1950. And a lot of lines here, but I want to focus us on 3 lines. The first is this top one. Let me make sure I get the thing figured out here. The top one here, this is coal-fired generation. And you can see going back to 1950, coal-fired generation started to dominate electricity production in the U.S. It peaked in about the 2007 time frame, and at that point it was about 60% of all U.S. electricity generation. So that's the first line. The second line is this lighter blue one that you see coming up, and that's natural gas production. And this is really a significant driver in what's happening in our energy landscape today in the U.S. Tremendous amounts of natural gas-fired generation being added to the system, and you can see for the first time in 2015 it actually surpassed coal generation. But one thing really very dramatic, though, is despite this long and steady climb in the share of coal generation, the drop has been really quite sudden and dramatic. And that's causing some of the same discussions in the U.S. that are happening here. In fact, our new Secretary of Energy has asked for a study to explore whether or not the retirement of coal units in the system is causing a jeopardy to reliability. And then finally, and this is the one that is most near and dear to me, is the green line coming on strong here in the last few years. This is non-hydro renewables in the system in the U.S. And I'll go into a little more detail about what's embodied in that line in a moment. But this is really the big driver right now in our energy system. This is the price of natural gas in the U.S. going back to January of 2000, all the way over on the left-hand side. And you can see in the first part of the 2000s up through about 2007, 2008, a lot of volatility in gas prices, some very high spikes in prices. Despite this, some of the gas generation build-out started in this time frame in the U.S. For reasons I haven't had time to really go back and fully understand, but more gas units started to be added here. But then you can see some very high spikes in prices in the 2005 and in the 2007 time frame, and then this precipitous drop. And that reflects the advent of the hydraulic fracturing revolution in the U.S. From this point forward, you can see not only a reduction in price, but a stabilization too. Not quite as much volatility in the price of natural gas. And if you look at this green line, this is the average 2016 gas price, and it's lower than at any point in this century, with that one small exception. So this is fracking in the U.S. has led to really an abundance of gas supply and a commensurate downward pressure on prices. And this means that utilities are relying really on three sources principally. If they need to add capacity, they're adding natural gas and wind and solar. And this is what's happening in the wind market in the U.S. The blue bars in this graph are the cumulative deployment of wind in the U.S. This goes through 2015, and we recently have 2016 numbers in. It was a great year for wind in the U.S. We deployed 8.7 gigawatts in 2016, bringing our cumulative total to a little bit over 81 gigawatts. So really a lot of wind on the system. As a percentage, it's I think I forgot to point out one thing on this chart, which is just for some additional context. The overall size of the U.S. system is 1,100 gigawatts, so it's a big system. And even though the 81 gigawatts of wind is a very encouraging and large number, as a percentage, it's still not huge. Wind accounts for about 7% or so of generation in the U.S., which is becoming significant, and it's an exciting number to be able to report. So this is wind. This is what's happening in photovoltaics, and this chart is a little bit different than the previous chart in that these bars are not cumulative. These are annual, and I do this for a specific reason. There is actually one bar that's a cumulative bar, and this is all of the photovoltaics installed in the U.S. through 2009. And this is what's happening annually since then. So this is an exploding market in the U.S. As somebody who started my research in 1988 in photovoltaic materials, when the global manufacturing capacity was 50 megawatts, it's just very exciting to see this kind of market taking shape in the U.S. So 50 megawatts global capacity in 1988 versus 14 gigawatts installed in the U.S. only in 2016 alone. There's a factory, the Trina factory in China, I think is up to nearly 2.5 gigawatts. That's their manufacturing capacity, a single manufacturer. So this is a very exciting time. A line I didn't focus on much of the wind chart, but here in the solar, this is utility scale solar price decline. It's associated with the right-hand axis. This in itself is exciting, but what reports we're getting in the U.S. for early 2017 are prices below $1 a watt U.S. for installed utility scale systems, which is really quite the benchmark. Back in the early days of when I was a researcher in PV, this $1 a watt kind of number was our long-term sort of stretch target. Maybe we'll see it in our lifetimes, maybe we won't. But it's still, I'm pretty young, and I'm seeing it, and I feel pretty young, and it's so exciting to see this actually happening. So that's what's causing that transformation that we saw in the first chart. Very low and abundant very low natural gas prices, abundant supply, and a rapid improvement in the cost of wind and solar. Coupled with, underpinned by a lot of R&D over the years, continued improvement in performance and reliability, and reductions in manufacturing costs for the components of these technologies. So a little bit about the grid. For those, sorry, I know, I'm sure a lot of you in here understand very well about how grids operate, but I found that a number of talks that it's not... It's helpful to go over a little bit to understand why it matters that wind and solar represent challenges in integrating them in large numbers into the system, into the power system. So the U.S. power system is broken into three synchronous interconnections that are depicted here. They have not very creative names that we refer to them. This is the Eastern interconnection. This is the Western interconnection. And the source of a lot of joking in the U.S. is Texas has their own. It's called ERCOT. They at least have a different name for it. It's the Electricity Reliability Council of Texas. And this looks pretty straightforward, but if you overlay onto these three synchronous interconnections the market and utility operating framework, it gets a lot more complicated. We have every sort of conceivable operating paradigm in the U.S., all the way from completely vertically integrated regulated utilities, and that's you find that mostly in the western U.S., a little bit here in the southeast, to wholesale markets like you have here, and is the most comparable market, as I understand it, is with that market in Texas, with ERCOT. That's the most comparable in the U.S. to the Australian market. So with this sort of patchwork of different operating paradigms and regulatory schemes and market schemes, it's just an added layer of challenge and complication in trying to facilitate a transformation of the system to a low carbon system. And a couple quick words about conventional utility operations. It's an amazing machine. I mean, I never cease to be fascinated, if you think very much about it, that the light comes on actually every time you flip the switch, or pretty much every time. Very reliable systems. Utility operators do a remarkable job in that there's actually very little storage in the system, so that means at any given moment, literally second by second, supply is being dispatched to meet demand. And it's a remarkable engineering feat that's able to be done on the kind of scales that we're talking about, especially day in and day out, all year round. And it takes something very dramatic to happen to really knock them off their game. Something like a major storm, for example, just a reference you might be familiar with. So this is how utilities have operated conventionally. Here's a day-long demand curve. This happens to be from the actual data from the western U.S. So pretty intuitive. The lowest demand is overnight, and as people get up in the morning, the demand increases, and then as businesses close and people go home, there's a little dip, and then the peak happens in a lot of places as people get home and start doing all their cooking and running dishwashers and doing laundry and so forth. And so part of the message here is that utilities are accustomed to operating a system that's variable and uncertain. The demand varies throughout the day, increases in the middle of the day and then peaks in the evening and drops overnight. So it's variable. They're very good at predicting that, actually, but they're not precise at predicting it. So there's some uncertainty in the demand throughout the day. And so they have to pay very close attention as the day moves on to exactly what the demand is. And of course, a lot of this is automated now, but they deal with that variability and uncertainty on the demand side historically by dispatching the conventional generators. These are, yeah, that's all lined up right. So they know the shape of the demand curve, and they dispatch their conventional generators to meet that demand. So what does wind and solar do, though, that makes this such an interesting problem and such a challenge? This shows 6 days, just like that one day I showed before, and this is the line that I talked about before, and it has that similar shape. And this is what utilities are historically operating to. But because wind and solar have zero marginal operating costs, the fuel is free. Utilities, if they have wind and solar in their system, always want to take the wind and solar. So that means they're starting to operate now the rest of the fleet meeting a net demand curve. So the net demand or net load is load minus wind and solar, which is in this green line. And so now when they're managing the rest of the fleet to the net load, it's this line right here that's that's on top of the orange part of the curve. And so that you can see just a quick visual here. That's a very different operating paradigm. It's you can see that often just the regularity tends to disappear a little bit. Some of the ramps become much steeper. There can be multiple peaks during a day that you didn't have before. Peaks can be shorter, and importantly, a lot of times you have to turn down your conventional generators in ways that they weren't necessarily designed to do, but are capable of doing, but certainly in ways that they're not accustomed to doing. So anytime you're moving away from your tried and true, literally century-old operating paradigm to something that's really quite new and different and challenging, there are hurdles to change always. So this is why wind and solar matter. And the more you get on the system, the more this net load line changes. And you can see here in this one case, the net load actually turns out to be close to 0. So now I want to talk to you a little bit about some of the research we do to try to understand what this means to power systems and if we can continue to operate them reliably as the penetration levels go up. And in a lot of ways, you all are globally speaking, right out on the tip of the spear, for better or worse. I mean, South Australia has some very high penetrations, instantaneous penetrations that are really quite impressive, but annualized as well. I want to talk to you a little bit about a study we did looking at the Eastern interconnection in the U.S., which is one really large machine. It's the largest synchronized power system in the world. But it was built around conventional technologies, the historic way that systems were built and run, large central generation, transmission, distribution with dispatchable generators. But it's changing, as I showed in the beginning. The generation technology mix is sort of rapidly shifting away from very large central generation to a much more diverse mix, including variable generators, wind and solar. Can get it to stop on this one. So these are some of the characteristics of the Eastern interconnection, and part of what made this study really a very significant challenge. It's a really big system, 700 gigawatts of generation, over 7,500 generators. It services about 70% of the U.S. population, because just like Australia, our population centers are more weighted to the eastern seaboard. One of the things that we were really focused on is the number of nodes. Those are the number of transmission substations in conventional utility operations. Operating a transmission system is the objective is to basically get the power to meet the demand at each of those substations throughout the day, every day. So that was a challenge in our modeling. Is we wanted to we asked ourselves the question: could we operate the Eastern interconnection with 30% wind and solar, which is about 3 times what's on the system now? And so to do that, we had to first build out that system in a modeling environment. So we took kind of a 2-step process. We have capacity expansion models that allow us to, the model, first I'll say the model has the current system in it, so it knows what generators are in the system. It models every generator and every high voltage transmission line. So it starts out with the existing system, and then we tell it what we think the load is going to be in some future year. And the model year here happens to be 2026 for a variety of reasons linked to the way utilities planned and some of the data that was already available to us. And for the capacity expansion model, we tell the model that already knows what the existing system looks like, what the demand is going to be in 2026. And then in a cost-optimized way, it builds out additional generation capacity and transmission capacity to meet that demand. So we did that, and we constrained it on the front end, though, to say, build it out in a cost-optimized way, but do that in a way that makes sure that 30% over the course of the year, 30% of the demand is serviced by wind and solar. So the model does that. It builds out that system in a geospatial fashion. It actually locates plants in the country and builds transmission lines to interconnect those plants when it needs to. And then after we have that modeled system, we import that system into a production cost model. And that's the model that actually dispatches the generation to each of those 60,000 nodes. And this is a fun part of, particularly here, of telling about this part of our work, because we've done this in very close collaboration with a company out of Adelaide. Energy Exemplar is the producer of a model called Plexos, and we picked Plexos and Energy Exemplar partially because they're very bright people, but also they had a production cost model that allows us to do dispatch on 5-minute time intervals. Most production cost models do hourly dispatch, but the wind and solar change a lot during an hour, so we needed a higher fidelity, we felt like, to really be able to start to understand better what was happening under these higher penetrations. And so we partnered with them to do that. It was actually turned out to be a little bit of a wilder ride, I think, than most of us expected because of the computational intensity of this. When we did an estimate, so just to back up for a second, what we're doing with the production cost model is we have now roughly 7,500 generators and 500,000 miles of transmission line. And for the entire Eastern Interconnection, we need to dispatch that every 5 minutes to meet demand in a least cost fashion. So the Plexos is an optimization model as well, cost optimization. And that's what utilities do in real life. They figure out ways to dispatch their existing generating fleet to meet demand in the least cost way they can. So we're doing that, though, trying to meet demand every 5 minutes with 7,500 generators and all that transmission to 60,000 nodes. And so our first estimate of running Plexos on a laptop to solve for 1 year was going to take 545 days. So that was kind of a non-starter. If you're taking 1.5 years to solve for a year, you're probably going down the wrong path. So we worked carefully with Energy Exemplar and our scientists at NREL to partition the code. We broke it up into 72 pieces temporally and ran it on a supercomputer that we're really very fortunate to have. We have a petascale computer, so 1 trillion calculations a second. So doing it on that, breaking it, partitioning the code and running it on the supercomputer and knitting it back together still takes 19 days. So it's a very computationally intensive exercise. Part of that's because of the data sets that we have that feed into it are enormous as well. We have our wind data set, for example, is on 2-kilometer grids for the entire country every 10 seconds. We have wind speeds on a 2-kilometer grid every 10 seconds. Solar's a little more coarse than that, but still really, really large data sets. And the demand data, too, at all 60,000 nodes is a pretty substantial data set as well. But we were able to do it working with Energy Exemplar, and we ran the production cost models, and we were able to simulate the operation of this system for the entire year. And to shortcut the answer, 3 years of work, a 250-page study, is the answer is yes, you can operate it. So a lot of what we do, I want to interject, we focus a lot on what's technically feasible. We want to inform the discussion by talking to policymakers and regulators about what's technically feasible. I mean, if you create the right kinds of policies, the right kind of investment environments, if you can establish the kind of markets that are going to reward value to the system, this is what you can do technically. And I think we feel pretty comfortable that we've demonstrated in these kinds of studies that you can start to integrate a fair amount of wind and solar into the system and operate it reliably, and without adding, at least in the near term, any storage. Our models in this particular case and in a number of other cases that we've worked on have not built out storage at the penetration levels we've studied so far. So we feel pretty comfortable in saying we can get up to 30% annual penetration without adding storage as a requirement to maintain reliability. So we actually did four scenarios because we didn't take 540 days. We could do only 19 days. We could do more scenarios and explore the parameter space a little bit better. This is the kind of the most interesting one here. This is the first one we did was as the baseline case. You always do a baseline case. It was as the system existed in 2012. We did a 10% penetration case and two 30% cases. One of them was where we constrained the capacity expansion model not to build out transmission, so that within each region they had to meet their 30% criterion within each region. So very minimal transmission build out in that case. But in this case, which is the 30% interregional, hence the IIT, interregional transmission, 30% case is the model was less constrained and was able to build the wind and solar where it thought the resources were best, and then build transmission to get that to load. And these are just depictions state by state. The darker the blue, the more wind that got built, and the darker the orange, the more solar that got built. It's one of the interesting findings, and a pretty consistent finding throughout a number of these studies that we've had, is that transmission is critical. Transmission is a robust and well interconnected transmission system is vital to adding flexibility to the system and for moving power around where you need it, when you need it, especially if you have variables on the supply side, variable generators on the supply side that may at times be producing more than you need in that particular region. You can ship it elsewhere. You don't have to curtail it. But transmission adds flexibility to the system, and flexibility is key for integrating variable renewables. That's really actually probably the most important common denominator, that the common thread between all of these studies is that flexibility in the system is what is key, and identifying accessing economic forms of that flexibility is what's really quite important for integrating high penetrations of wind and solar. So here's some annual results. Nothing too surprising. This shows the generation mixes for each of the scenarios. This is the 2012 grid, the 10%, and the regional transmission and the interregional transmission. I mean, the first thing that's obvious is that wind and solar displace gas and coal. Zero marginal costs again for the wind and solar because the fuel is free. The fuel is not free for gas and coal. So that's what tends to come offline first when you have a lot of wind and solar. And then the 30% that I've been talking about all this time is an annualized number, and that means that as you all have experienced here, in sort of world record kind of numbers, an annual number means that there are going to be times when the instantaneous penetration can be quite a bit higher than that. It's reached all the way, as I understand it, 119% in South Australia, 119%. And in this case, with 30% in the eastern interconnection, the highest instantaneous penetration we saw was only 60%, only being within the context of 119%. 60 is huge. 60 is really huge. And curtailment, we found, too, would be within range. A lot of times, when I talked about turning down the conventional generators, sometimes you can't turn them down anymore. There are a number of regulatory requirements about operating reserves and contingency reserves that you have to have online, and so you just can't keep turning everything off, or else you'd be in violation of your reserve requirements. And so you get them down so low at times, and at periods when there's very low demand and very high wind and solar, that means you end up having to just spill the wind and solar. You don't get to bring it onto the system. You turn inverters off, you feather wind turbine blades, or whatever the case is. And one glimpse at this issue here of what transmission does for you, you can see over the course of the year in the low transmission build-out case, there's about twice the curtailment as you see in the case where there's transmission, much better interconnected transmission. And so this is the way we have historically looked at some of the results of these studies. These are, again, dispatch stacks of the 4 scenarios. This is as it was in 2012. Kind of familiar to utility operators. You see sort of the regular nature, the smooth up and down variations in the demand and the associated dispatch. Changes a little bit with the 10% case, but not that much. Still looks pretty familiar. But once you jump to 30, this changes quite a bit. And you see a lot of those features that I was talking about in the slide, trying to articulate why wind and solar matter in the system to operators. You can see that a lot of the regularity starts to disappear. Ramps get steeper. We picked this day. We're always looking in these studies at the very worst days. I really have to point this out because not every day is like this. This happens to be a very low demand, very high wind day, high solar as well. That tends to happen in the springtime, I think, in a lot of places. But it really does change the environment for the utility operator. You can see a little bit more about that curtailment here. A lot more curtailment in the limited transmission case. A little bit less here in this case, but most of the days are not this raucous. Okay, thank you. They'll look more like this. When the demand is high, the wind and solar get more easily absorbed, and those ramps don't appear the way they do in this dramatic case down here. So I don't have videos here just to simplify, to be able to email it first, because with the videos in, you can't email. But if you're interested in this, we have the study itself has its own website, nrel.gov/urgis, the name of the study. But also on YouTube, you can find this stuff on YouTube and watch these things until your heart's content. They're animations of the system running on these 5-minute intervals. And what you see in it, it's pretty cool to watch them, at least I think so. The size of the circle is the amount of generation. So every generator in the Eastern Interconnection, and this is all the solar that the model built out. The color is the type of generator. And so as it's running, you can see the generation changing on 5-minute time steps. We have it so that you can see the sunrise. There's a sort of a lighter and darker line that moves across. And when that happens, a lot of the wind in the wind belt when the sun comes up, tend to settle down. All the solar generators fire up. You can see natural gas coming off and on, coal being turned down. And the arrows show how the power is flowing. That was really one of the things the visualization made us appreciate a lot more. Again, the importance of the interconnectedness of the system. And that's not something that really happens very much in real life right now. There's limited trading between regions. And we even, to try to reflect that, we put hurdle rates in being able to get power from one section to another to make it more expensive, so it wouldn't do it as much. But still, to manage the system, it requires a lot of cooperation in between the markets. And that takes transmission. And this is another type of animation. These are all on the YouTube channel as well. That shows how power is flowing. These pinwheel diagrams are changing on the same 5-minute time steps, and shows how the power is flowing from region to region. And a couple of real-life examples in the U.S. These are some of our highest penetration levels. This is my home state of Colorado. This is where the National Renewable Energy Lab is located. We have a lot of wind out on the eastern plains. We're part of the wind belt, which runs in this region of the country. Some of the best wind resources there, capacity factors in the mid-40s if you build out wind plants in that region, so very good capacity factors. But we have an annual average wind penetration in Colorado of about 17%, and there have been several periods now, even since October of 2015, where they've operated for 24-hour periods with an excess of 50%. And they're very proud of that. They issue press releases, it's because it's all transparent to us. They're able to do it. The lights stay on, and it's honestly very exciting to see that. And this is even a bigger footprint. This is the Southwest Power Pool in the Eastern Interconnection, and this happened very recently. And I'll leave my discussion of integration with what to me was a very inspirational quote from the person who's responsible for operating this system, making sure this system stays reliable. The Vice President of Operations said that 10 years ago, we were concerned about 10% penetration. We thought that was going to be a real challenge. We thought 20% at that time would be a serious, would put our reliability in serious jeopardy. But in February, we did 52%, and it's not even our ceiling. So the thinking on this is changing very rapidly. That quote was particularly satisfying for me because I had started doing this myself about 10 years ago when 10% made people very nervous. I mean, many utilities at that period would say 20% impossible. And now 20% is a given. I mean, they don't even think anymore about 20%. People are starting to think about 30%, 40%, 50%. And so it is changing very quickly. And a lot of this, I think, is, our studies have at least been one little component of the discussion, but working very carefully with them to structure these studies and execute them and pore over the results has allowed them to find economic sources of flexibility that they really hadn't had to consider before, but they're there. And we've been working very carefully with them to identify them and access them. And that's led to some of these higher penetrations in the U.S. So I'll jump now a little bit to a very quick discussion, because I'm running low on time, of some of the policy drivers in the U.S. that have caused wind and solar. Be critical in the U.S. is that we haven't had very stable or steady federal policy framework. I'm not sure why you're laughing, but I'll no. All the action, even historically, through a number of different administrations, the action happens in the states. I mean, there have been a number. We have no federal portfolio standard or clean energy or renewable energy target. They've been introduced repeatedly in the Congress, but they've never made it out into law. So the states have sort of taken matters into their own hands, and that varies quite a bit. Again, it makes for a difficult environment to try to make sort of broad-based change, but it's been, the orange states all have standards or requirements for renewable energy. The yellow ones have targets that are non-binding. But we spend a lot of our time in the analysis center trying to understand the impacts of these portfolio standards. And so we broke apart what the red line represents all of the non-hydro renewable generation since 2000. And the blue line is what we determined was the contribution of the state portfolio standard. So obviously a major driver for deploying wind and solar in the states. We spent a lot of time as well trying to understand and quantify what some of the benefits and impacts were. All of these things I invite you to go find on our website. They're all available studies, free to download. So we focused a lot on greenhouse gas and particulate emission reductions attributable, because we want the policymakers to be able to see and understand what the impacts of these policies were, and to help inform the discussion of future policy frameworks. Very interesting here is trying to quantify some of the economic development impacts, and they're really substantial. A very important assessment of jobs in the energy sector came out earlier this year. 300,000 people in the U.S. right now working in the solar sector. About 150,000 in the wind sector, even more. So nearly 500,000 people now employed in wind and solar in the U.S. So that's a big number. That's exciting. And just for some context, in the U.S., there are 150,000 people employed in the entire supply chain of coal, from extraction to transport to operating power plants. So 500,000 in renewables now, 150,000 in coal. You would never actually know that from the political discussion, but those are the numbers. We like to deal in data. The federal government has not been absent, though. I want to make sure that that I make that point. There have been very important tax credits, and I put this up here for a couple of reasons, but principally to show that in 2015, when there was a discussion of whether or not to extend the solar tax credit, which was going to expire in 2016, the wind tax credit had already expired at that point. We got to be involved. This was a very exciting a few-week period here, but we got to be involved in helping some congressional members understand different scenarios that they were considering in extending the tax credits, about what the implications were for uptake of wind and solar in the market, and what the implications might be long-term for emissions if they didn't pass the standard. So that led me to the conclusion that these tax credits were actually quite important in supporting wind and solar market development. And this is, in one quick shot, you can see what happens here. The wind tax credit, the solar tax credit had been passed for a number of years and was pretty stable. The wind tax credit got discussed every single year. And some years it got passed again, and some years it didn't. And you can see what happens in the investment and the project development business when it didn't happen. And the industry just kept saying, tell us what it's going to be and then keep it that way, because we need the certainty. When there wasn't the certainty and it got rehashed every year, anytime it had expired, nobody would build anything because they thought there was a good chance that the next year it was going to get re-implemented, and why would I put my money into a plant when I can just wait and get the tax credit? And so that's why you see there's no better example here than to illustrate the importance of stability in policy. So anytime you ever get a chance to potentially talk to representatives, it matters a great deal to the investment community in particular to have that certainty and stability. So I need to wrap up here. I think I've probably hit most of these points, but just to drive them on home, policy is critical. We would not be anywhere close to where we were today if there weren't policies in place that supported wind and solar development. And that policy stability is sometimes as important as the policy. I know the industry has thought that often. Federal policies are important, but state level policies really in the U.S. have been the principal driver. Policies have worked in a number of ways, but they've worked in tandem with a very robust research and development agenda. They worked in that they provided a market. They began to scale up. You're able to mature supply chains. You're able to attract investment in that scenario. But through research and development, we've also been able to continue to improve the technology and reduce the manufacturing cost. And then related to a major takeaway for me related to integration is that a growing body of research suggests that you can get a lot of wind and solar into the system and operate it reliably. And the key is finding flexibility in the system. And because we don't go from 0 to 100 overnight, we have time to identify those economic sources of flexibility that already exist. And then as we get higher and higher in penetrations, we have aggressive storage research agendas, for example. Storage can start coming online as penetrations really increase. And then a lot of where we spend our time is in this. We, as I said before, we look at what's technically feasible, and we know that there is a tremendous amount of value in terms of reliability support and resiliency support that these new technologies can bring to the grid, but there's a real misalignment right now between what's technically feasible and what markets will support and value and what regulation often allows. So helping policymakers to understand that and to hopefully accelerate the alignment of the technically possible and the regulatory and market frameworks is going to get us farther down the road to decarbonization even more quickly. So again, a great honor to be here. Really appreciate the chance to speak in this wonderful place, and thanks for coming. I really appreciate your attention a lot. Sure. A few minutes over.
Now we're going. Dr. Mooney's prepared to take questions, and we've got a fair bit of time allocated. So, when you, they're all eager. When you ask your question, could you please indicate your name and if you have an interest in terms of employment or an organisation, you might like to mention that too. So
Yeah.
first hand up the back in the white shirt. Yes.
My name's Rob Thomas. My name's Rob Thomas. I'm an environmental advisor on major mining projects. My question to you, David, and thank you for that talk, very interesting. Is there a limit, did your model reveal a limit on the penetration without storage?
Not at this point. The one thing I can say is that in the U.S. system anyway, most of our research suggests that we've got quite a lot of headroom still to keep adding wind and solar. We're only at that 10% kind of mark nationally. Regionally, it can start to vary. One thing that our studies did do, though, is make quite a bit more use of the storage that's already in the system in following the ramps. And the storage that's in our system right now is about 23 gigawatts of pumped hydro storage. Pumped hydro has been around for a really long time. It's very reliable, it's very efficient, it's very cost effective. So our production cost model uses that storage more, but we didn't find it necessary at this 30% level to build out any new storage. We've done some work for California where they have a portfolio standard of 50% at this point. That's published under the title of, I think it's called the Low Carbon Grid Study. And we did include, they have a storage mandate in California of 1.3 gigawatts of electrochemical storage. I think they actually disallowed pumped hydro because that's sort of old news, and this is, it wasn't as much, this initiative, this is my own take, this initiative wasn't as much about ensuring reliability with that 1.3 gigawatts of storage, but it was to get utilities to start understanding how to integrate that storage into the system and be prepared to use it when it was necessary. So we included that storage along with the pumped hydro that exists in California already, but we were able to go to 50% without having to build additional storage beyond that. But I think as you start to, things really start to look like they more radically change at the sort of the 50% threshold. So once you start getting up above that level, and this is the annual average number again, 50%, it looks like it's more likely storage will have to be considered. But right now we consider, when we lay out all of our flexibility options, and this is, I'm happy to send this to anyone or leave it here. This is a chart that, a bit of a backup chart that shows different sources of flexibility, and it's laid out sort of notionally here, that sort of the most accessible on the left, least accessible on the right of the x-axis, and cheapest at the bottom and more expensive at the top. But right now, it's our position that storage is going to be a vital part of the system in the future. We don't know exactly what that threshold is going to be because the threshold keeps moving, as the operating guy from the Southwest Power Pool said. But right now, we think storage is among the more expensive sources of flexibility. And there's a lot of different kind of storage too, it's important to note. Thermal storage is not that expensive. If you can do solar thermal, that's much closer to cost competitive. I think there's a lot of promise in technologies like hydrogen. We have a very active hydrogen program, making hydrogen when the wind blows excess and the sun is generating excess. You make hydrogen with it. It's a very flexible fuel. You can convert it back to electricity. You can power vehicles, any number of things. So it's a pretty complex landscape, a lot of options. Finding the pathway there that maintains reliability at a good cost is the key.
Muriel, I think you were next.
Thank you very much. Thank you. That was a really interesting talk, David.
Thank you.
In your two 30% scenarios, you had one which was regionally constrained and one where you had the interconnects.
Yeah.
I noticed that the solar penetration in the regional constrained one was much, much higher than it was in your interconnected one. Can you provide any feedback on why that would be the
Yes,
case?
it's a very interesting aspect to this that we've seen in a number of studies actually, and that is at the time we did this study, wind was still quite a bit cheaper than PV when we initiated this study. You know, this is one of the hard things in such a dynamic market and technology landscape, is that by the time you do a study that takes this long, you lock down your prices, and then by the time you actually publish it, those are very much out of date. But when we started and locked down our technology prices, solar was more expensive than wind, and that was still projected to be the case. So what our models do and show this over and over again is that it's cheaper to build renewable resources that are capital intensive where the resources are best and build transmission to where the load is. And that's what the model did in this case. It built, when transmission was constrained, you had to build out a lot more resources by the load, and that meant a lot more solar got built out. When transmission was unconstrained, it built out a lot more cheaper wind in the wind belt, and it was cheaper to build transmission to get that wind to market.
Over on this side, yep, you. Looking for the microphone.
Thanks, that was a great chat. My name is John Silopoulos. I'm a technical manager for iron making for a steel company. I wanted to know the graphs you presented, the long-term graphs you presented about power generation sources show that, according to your graphs, the hydro and the nuclear plateau in about 1980.
Yep.
And all the scenarios you ran had they had them as constants pretty much.
Right.
The hydro you had in that constant amount, was that, you talked about stored hydro only after the presentation, so that's just hydro without storage?
Yeah, the blue line in there is conventional hydro, large-scale hydro in that chart. So that's right. Doesn't include the pumped hydro.
So, and the question was, are you doing runs, or have you done predictions with the nuclear removed or expanded or decreasing?
Yep.
And what's replacing it?
So we did quite intentionally leave the nuclear alone. Basically, we left the nuclear to run as it has done historically. We have it's about 20% of our overall power supply in the U.S. We have about 101 operating units right now, so really quite a lot of nuclear. But generally speaking, we left them alone to run the way they run now, which is flat out. We do build into the model the times when they have to shut down for maintenance and all those kind of scheduled maintenance things. But we left all the nuclear there, even though we only retired plants that, and this was applicable to coal as well, we only retired plants in the model if they were already announced to be retired. We left everything else in place.
Hello, thank you for your talk, David.
Yeah, you're welcome.
My name is Hai, and I'm from University College London, Australia. My question is related to your position on the relative role between natural gas and renewables in America, especially in the context where shale gas boom is taking place dramatically in America, and we have the case of Texas where shale gas production has increased significantly in the last few years,
Yeah.
and also they have installed a large amount of renewable capacity as well.
Yeah.
So do you think that the shale gas boom, or in general, the role of natural gas is hurting or helping renewables?
Well, it's a great question, and depending on what aspect of renewables you're considering, the answer is yes and no. When we have our deployment models, that rely a lot on the cost of technology. When we do capacity expansion that way, the largest sensitivity that we find to gas or to wind and solar getting into the market is the price of natural gas. If natural gas prices are high, more wind and solar get deployed. If natural gas price is low, the way it is now, gas is likely to get built ahead of wind and solar. So from that perspective, it's bad. But where it's good is that natural gas generation in the system, a system that is more heavily reliant on natural gas generation, is much more flexible than a coal-based system. Natural gas units can turn on and off. You can turn off a lot of natural gas units. You can't. It takes sometimes days to turn a coal unit back on, so you can't really turn those off. They don't ramp as fast as natural gas. So what the proliferation, I can't say the word, the advent of more and more natural gas onto the system in the U.S. has made it more flexible, allowing the accommodation of additional wind and solar. So that, from that perspective, is very good for renewables. And I think it's also, if you look at our emissions profile, it's caused a decline in our emissions quite a bit faster too. But despite that comment I made about our model showing low natural gas prices mean not as much wind and solar get built out, because of the other policy frameworks that are in place, the last 5 years, the top 3 capacity additions in the U.S. for the last 5 years have been wind, solar, and gas. And for 4 of those years, wind and solar have beaten out natural gas. So more wind and solar going on than anything else right now.
On the front here.
Keith Potts, I'm the lucky one, I'm retired.
Yes.
10 years ago, there was a significant increase or interest in geothermal energy in Australia, and very specifically in South Australia, and it all disappeared. I, along with many others, lost money on the research, let's say, and it never proved to be viable. But geothermal is used in some countries, Iceland, for example, and I believe also in the US.
Yep.
I mean, is anything happening with geothermal in the US?
Well, we have a research program at the lab that's actually growing a little bit. We had geothermal production in the U.S., or capacity in the U.S. had gone stagnant for a number of years at about still a decent amount, 3.5 gigawatts of geothermal production in the U.S. And we've recently finally brought some additional online. It's up to about 4 gigawatts right now. I think it gets too little attention because it offers the promise of a carbon-free baseload generation, and so I think it could be a very valuable part of the grid from that perspective. In the U.S., the reason conventional hydrothermal geothermal plants have not gotten built is that it's hard to get financing to drill the holes, because the risk for drilling the holes and coming up dry has proven to be very high. And that's my understanding of why development hasn't proceeded at a pace. We have a great resource in the U.S. as well, as you do here. We also have an active research program in enhanced geothermal systems, which some people are trying to leverage some of the techniques used in fracking for gas to go to hot, dry rock and frack that rock and force fluids down. And the capacity potential for that technology, if it could be proven out, is much, much higher than conventional geothermal. But I think there are great arguments for a continued research agenda for geothermal because of the value that it could add to a carbon-free system.
Could I just ask one more question about nuclear?
It's okay with me.
Do you expect the US will replace the nuclear power stations as they come to the end of their lives, or build even more? What's the feeling there? Because here there is politically zero chance
No,
of
this has
building
been an
nuclear.
interesting education for me since I got here, appreciating that it's, it just basically you don't talk about it. It's not an option. But the hurdles, kind of the societal, cultural hurdles in the U.S. are very high as well. I mean, a lot of that got built out, as was noted, through the 80s and into the early 90s, and we've been sort of going along at 100 or so gigawatts ever since. We have added, for the first time in 2015, a new reactor came online, but that was built at the site of an existing reactor. I find it, now I'm getting into just sort of pure opinion here, but I find it very difficult to imagine a greenfield site being permitted and built in the U.S. There's just there's a tremendous amount of opposition of people not wanting that in their communities. So what is happening, though, is plants are being run well beyond their initial projected lifetime. They're being maintained. They're run remarkably safely. We don't have anything to do with the waste from them because of politics mostly. There was a project that received many decades of study and, or maybe I should just say years of study, many tens of millions of dollars to bury the waste in a place in Nevada, in the state of Nevada, but that was never adopted. So that's another really significant issue, is what to do with the waste. Right now, it's mostly being stored on site at nuclear plants. So I don't think that we're going to see any really major growth in the nuclear sector. Let me just, as I say that, one more quick note on that is that small modular reactors could change the game a little bit, I think. The Nuclear Regulatory Commission is looking at several small modular designs, and so instead of being gigawatt plants, these are hundreds of megawatts. Some of the designs are completely underground. Some of these could change things. They could also be made potentially more flexible than the large plants.
I think we've got three people still waiting for questions. So can we have a question that invites a quick response? And
well,
we're running
that has a lot to do with the guy answering the questions. So I'll try to.
1, 2, 3, 4. Sorry, Bassam, you're too late. You'll have to answer your own question later.
I'm P. I'll try to make this quick. I work for a distributed energy company. So one of the big problems we have here was with market structure. The market is slow moving.
Yep.
Reform is very slow moving. Even things like the move to 5-minute settlement are going to take a good 2 years to work into the marketplace here. What I see happening in the US and I see happening here is a lot of small companies that are trying to experiment with new types of markets. But they're all having to do that on private copper. They're all going behind the meter to embedded networks, and they're doing all the crazy things: nodal pricing, peer trading, digital exchanges, blockchain, all this crazy stuff. Are there any examples in the US of those kind of people being able to break out from behind the meter and go to, is there maybe like a kind of like a special economic zone for a grid or something like that in the US where there's more room for market experimentation? Because it's sort of hard to get that going here.
No, it's same in the U.S. The progress is very slow. There is no special zone to be able to do that kind of market experimentation. But I would say that our study was a transmission operations study, but we also do a lot of work below the transmission substation in the distribution system. And my feeling really is that this is where there's going to be a tremendous amount of action in the future. Certainly technically, there's a lot of possibility there for real disruption in the way the power system works and how people consume their power and the relationship to utilities. I think the distribution system is where a lot of that action is going to be.
Alan.
David, thank you for your paper. I have a question which is unusual in terms of the context of... Thank you. I have a question which is unusual in the context of all the questions thus far. And firstly, unless someone gets me wrong, I'm a farmer. I know the climate is changing.
Yeah.
But my question is more to do with the humanities side of things. there must have been trillions and trillions of dollars spent on the renewable energy sector, wherein the problem which one is trying to fix is CO2 in terms of impact on our environment.
Mm-hmm.
Why has not been more money spent on trying to fix the CO2 issue from a chemical perspective? I'm not talking about carbon capture, but from a chemical perspective, breaking the bond, working with the physics and the chemistry of CO2, and make that into something else.
I do know of some research that is going on. Why that hasn't been the historic approach is I don't know if I even have a good speculation. I welcome any other comments on that. It really could be. I think in part the dynamic is I might associate it with what happens with efficiency. I mean, everybody recognizes that efficiency is the most accessible and the cheapest, most economically rewarding way to reduce carbon. Yet people are much more attracted to technology for some reason, for putting that solar system in the ground or on their roof. And that's been a really odd dynamic, I thought, over the years in the U.S. market. Even though we've been able to demonstrate for years, if not decades, the economic benefits of energy efficiency, but it's been so hard to get that in the marketplace. So I don't know if I'm not sure I know enough about the chemistry to give a detailed answer for why that's not true. But there's a lot of politics wrapped around and a lot of social and cultural elements wrapped around what we decide to invest in research and development. And I think solar and wind has solar especially, I think, has that sort of magic associated with it that really intrigues people. That's probably a completely unsatisfying answer, but that's the thing.
Benito Cao, I'm a lecturer in politics, and I want to thank you for a presentation that a non-engineer could actually follow and understand. That was brilliant.
Oh, good. Thank you.
I would like you to comment on the impact of the Trump administration on the energy picture in the US, and also specifically on how realistic you think is his desire or his policy of trying to revive the coal industry.
I think that I'll talk more in terms about what the consensus seems to be that's emerging from a variety of different analysts and experts. But most people believe, I think, that because of what's happening in the natural gas markets, that it would be very difficult to have coal make a significant comeback. Certainly, there are things that could be done at particular sites, perhaps. But I think most analysts believe that it's going to be, the market forces are just too strong. And in fact, in wind and solar too, I think the momentum right now is really potent. There's broad-based public support for renewables. Many states keep increasing their targets. And the cost of the technology now in many places for solar and also for wind, unsubsidized, has reached grid parity. And so I think the momentum is too strong to be derailed. I don't think, I think that it would be a better environment if we had a very supportive and consistent message at all levels of government. But even in the absence of that, I think the momentum in the technology and the public support for it is going to keep this transformation underway.
Very last question, Chris.
Generously donate my question to Bassam, actually.
Bassam Dali, University of Adelaide. I really wanted to extrapolate for your findings to South Australia, in particular, sort of where we have such a resource, a good resource,
right.
wind and solar. Am I reading that if we sort of forget about market for a minute and look at the national interest, what you're saying is actually building more solar thermal, for example, in South Australia, and having an interconnector to the rest of the country is the more optimal approach than what we're doing today?
Yeah, I think that would be something to seriously consider. I mean, I've in a number of discussions here, I've started thinking that I would love to do the analysis of comparing the the reliable operations of a grid under a number of different scenarios, but also with the economics of realizing that grid. And one of them would be, and a lot of our studies do show that quite an economic source of flexibility is in a better transmission system. So having South Australia, I'd like to look at the scenario where perhaps a lot of storage is built out in South Australia to maintain grid stability and reliability, and look at the operations of that grid, compare that to the cost and operations of better interconnecting South Australia to Victoria and New South Wales to see if to see which one makes the most economic sense.
Okay, well, thank you very much, and thank you for your generous time in
No, you're so welcome. No, my pleasure entirely. Thank you very much.
Thank you very much. Thank you. Okay, well, it's now my pleasure to invite Professor Bassam Daly to thank Dr. Mooney for his presentation. Professor Daly is also one of the Centre's leaders, and he helped establish the Centre and has been Deputy Director since 2009. He's Vice President of the Australian and New Zealand section of the Combustion Institute and is a member of the Australasian Fluid Mechanics Society. For the last 25 years, Professor Daly has contributed to many research fields, including combustion science, aerodynamics, heat transfer, applied optics, computational fluid dynamics, and renewable energy, including wind, solar, and tidal wave. He's published more than 90 journal papers in leading international journals and collaborates widely with many national and international researchers. So I now invite Bassam to respond to Dr. Mooney.
Thank you, Susan. I'm conscious of the time and I won't be long, I promise. Before I proceed to thank Dr. Mooney, I'd like to thank two people who actually helped us quite a lot in making today happen, and that's our support staff, Louise and Roz. So we just brought you some flowers to say thank you. We jumped at the opportunity that Dr. Mooney is visiting Adelaide to invite him to deliver this lecture, and we're really pleased that he agreed. So things were done a little bit in a haste, and Louise and Rob did a fantastic job in putting it all together. Dr. Mooney, thank you very much for this stimulating lecture. It has been really informative to me, and I'm sure to many of us in here. And it is most befitting to the legacy and memory of our esteemed professor who passed away, and we really thank you for that. I certainly learned a lot from the lecture. I hope your message to our politicians, which I know you're going to meet few, of certainty and stability for the future would be really beneficial to all of us in Australia. I think uncertainty was unhelpful in the last 10 years. So we're really pleased to see that you could back also these with some numbers to show what uncertainty can actually cause to our grids. So on behalf of our centre, the School of Mechanical Engineering and the University in Adelaide, I thank you for delivering the lecture. I wish you fruitful discussions for the rest of your trip. And I want to put an open invitation on behalf of all of us to invite you again to come and visit us. I know there's a lot of similarities between what NREL does and what our centre does, and hence I could see a lot of collaboration in the future. So please come. We have a small gift for you and also for Susan.
Oh, thank you so much. So nice. Thank you so much.
No, you're most welcome. Thank you very much.
I have another talk.
And lastly, I'd like to thank you all for your attendance. I'll invite you again to come to the next news lecture. And please look at our new website, and if there's anything we could do to help the industry or individuals, please do contact us. So thank you everyone, and